Okay, so yeah, we're going a little bit out of order. After linear and then Bernoulli, Riccati, and Clairaut was supposed to be substitution, but that's kind of a standalone section anyway, kind of like this one. So it doesn't really matter. Like you don't need to know 2.7 to understand this. So Picard's method, again, is going to be dealing with the initial value problem that we've been looking at. Y prime equals some function f of xy with initial condition, when you plug in x naught, you get y naught. Okay, so we're going to kind of explain the approach, and then we're going to do an example, and that's pretty much it. It's pretty straightforward. So one approach would be to integrate with respect to x. And so now we get y of x. And if we want to integrate with respect to x, we need all of this to be a single variable, right? We can't do a multivariate single integral. So what we can do is get around that by introducing a t. So x is t, and then y will be defined in terms of t. And so now everything here is in terms of t on this side. And then we just do x naught to x, so that in the end, this integral on the right-hand side, whatever it turns into, will be a function in terms of x. Does that make sense? Okay. And then, of course, don't forget plus c on one of the sides. Now, since we know the initial condition y of x naught is equal to x naught, or I'm sorry, y naught. Then we know that if I plug it in, so if I plug in x naught to x, now we have this function, but this is interesting in the sense that some nice things happen. What's this going to be? I heard is 0. Okay. So then we have now that our initial condition is actually just going to be equal to this constant that we get from that integration. And so now, if we rewrite our equation, we have the solution that y of x is going to be this constant, which we just showed is exactly the same as y naught plus the integral from x naught to x of the function f of t, y of t, dt. So by plugging in this condition, we figured out that this initial condition, which was actually equal to y naught, in fact equals c. So replace the constant with y naught, now we get this function. Okay? So this is equivalent to the IVP. Okay, we're going to use this to kind of figure out what the solutions are going to be. And so Picard's method, it's a method of iteration. Starts with this equation. Okay? And so now we're going to suppose that y0 of x is an approximation to the solution y of x. Then the right-hand side of the equation, so this side over here, gives us a new function. We'll call it y1 of x. So in other words, y1 of x is going to be what I have up here. Y naught plus integral from x naught to x, f of t, and then we'll go y naught of t dt. And now this is a better approximation. If we want better approximations, we just repeat the process. So now we say y2 is going to be y naught plus the integral from x naught to x of f of t of, and then we're going to use y1 now, and we keep repeating. So basically, once you find the first solution, then you kind of plug it back into itself to get the next one, and so on, until we get as many as we want. In the book, in our section, I think they only ask you to do at most 4. Okay, yes?
Is the term next to the equal sign, is there always going to be y naught, or would it be the...
Yes, this is always going to be y naught. And so, in general, here's the formula then. So if we're following the same pattern, we can do this as many times as we want, right? And we're just going to have y naught plus the integral from x naught to x of f of t times y sub n minus 1 of t, because we're going to always plug in the previous function into the integral, dt. And then this is, of course, for n equals 1, 2, 3, etc. Okay, so this is the formula that we need to use. Okay? We just keep using it to get the next approximation. And sometimes you guys might be able to actually figure out the solution by looking, like as we look at each approximation, and start to see what the solutions are going to look like. And it's going to look like a series. And if you remember your series, your Taylor series, then you might be able to identify, oh, this is just really this. I see some worried looks over there. Okay. So here's the example. Let's say y prime is equal to y minus 1 with y of 0 equal to 2. And again, we're going to use Picard's method. To find y1, y2, y3, y4, getting a better and better approximation at each step. Okay? All right, so let's take a look at what's going to happen. So first, I'm going to write down our initial condition, which was x naught was 0, y naught was 2. And I'm also going to write things in this notation using this formula. So y sub n of x is always going to be 2 plus the integral from x naught, which in this case is 0. So I'm going to replace x naught with 0 right away. This is going to stay x up here. And now our function is y minus 1. Okay? But we're going to replace that with y sub n minus 1 of t minus 1. Okay, because in each step, we're going to use the previous y value and plug it in. Does that kind of make sense, that notation? Okay? And so now, let's get started. So y1 is going to be 2 plus the integral from 0 to x of what? 2 minus 1. Very good. And so we just get 2 plus the integral of 1 is going to be t. The 0 is going to drop. You understand that this is just going to introduce x's, right?
Yeah.
So it's just going to be 2 plus x. All right. y2 is going to be 2 plus integral from 0 to x of now, to start, replace this, just so that it makes sense, replace this function with t as your variable, okay? So it'll be 2 plus t, that's your y, does that make sense? So here's your y, and then we're subtracting 1. So it's still y minus 1. We're just using the previous y value in its place, and we're using t so that this definite integral makes sense. Okay, and so now we continue. This will be the integral from 0 to x of just 1 plus t dt. And so now we get 2 plus x, and then t is going to be 1/2 t squared, but that'll just become x squared over 2. Makes sense so far? Okay, let's do y3. It's halfway there. 2 plus 0 to x. And now again, here is our y value, so that'll be 2 plus t squared over 2 minus the 1. Two minus 1 gives us just 1. That'll become just x. This t goes to 1/2 t squared, or x squared over 2 once you plug in the bounds there. And then this becomes x cubed over 2, but then also times 3. And I'm writing it in this fashion just so that we clearly see a pattern here, because one is going to emerge, okay? Let's go one more step. So then y4 is going to be 2 plus the integral from 0 to x. Are you guys okay with me just writing 1? This 2 is always going to get subtracted by 1, right? So it'll be 1 plus t squared over 2 plus t cubed over 2 times 3 dt. And so now I get 2 plus x squared over 2 plus x cubed over 3 times 2 plus x to the 4 over the 3 times 2 is still there, but now I throw in a 4, right? And so there's your 4. 1, 2, 3, 4. Okay. Now, let's see. And you don't have to do this per se, but if you do recognize it, it's kind of nice to see what the solution is going to be. Let's see if we can write the general formula. So we have y1, y2, y3, y4. What do you suppose y sub n is going to be if I keep doing this? Well, we're always going to have 2. That's always going to be there, right? Actually, what do you guys see what sequence this is? What's missing? We're missing a 1, right? Very good. So why don't we do this? 1 plus, and then let's write it out. 1 plus x squared over 2 plus x to the third, and so on. And so if I write the series, this would be the sum from k equals 0 to n of x to the k over well, it'll be n factorial, but we need k's, right? K factorial, yes. So this is the solution, the real one, okay? Everything up until that point was an approximation. So if you think of the IVP, so we have this initial value problem. This first function, 2 plus x, is an approximation near this point, right? As we get to the second one, this 2 plus x squared over 2 is a better approximation for the solution at that point. Does that make sense? And as we keep going on down the road, well, now this is no longer an approximation. This is the solution to the IVP at that point. By the way, what is this? It's one of the three that you're supposed to know. I always remember, like, if you see every single exponent, like 0, 1, 2, 3, 4, that's going to be an exponential function. If you see terms missing, that's either going to be a sine or a cosine, right? Like if it's to the first, to the third, to the fifth, or if it's 2, 4, 6, 8. Okay? So as t goes to infinity, this is your solution for the IVP. Okay? Now, one thing I want to mention, this problem that we did wasn't so bad. Okay, and you'll see that there's not many problems to practice in the homework because they're all very similar. So once you understand how to do the method, it's not hard, but it can get kind of tedious depending on the functions that you're going to be integrating. And the second thing is, you're not always going to be able to just say, oh, the solution is really just 1 plus e to the x. Okay, so when it says to find y1, y2, y3, y4, you do just need to do, here are my 4 approximations. Does that make sense? Because you may not know what solution it's going to be. It may just be weird functions that you don't really remember, have a series for or anything like that. Okay, so that's 2.8.